Hi there, so this video is on section 6.2 and 6.3. Solving differential equations by separation of variables is covered in 6.2 and 6.3, but 6.2 is kind of solving very basic differential equations, and then in 6.3 it just gets a little bit more complicated. And then we're also going to be talking about law of exponential change, which is related to solving differential equations of this form. So until now, we've solved differential equations that are in the form dy over dx equals to a rule that's in terms of x, or f prime of x equal to a rule in terms of x. And then we've talked about how we use integration when we're solving differential equations. And when we find the general solution to a given differential equation, you have the plus c to represent the infinitely many possible values that c could take on, and the infinitely many possible antiderivatives that solution could represent. And then a particular solution means that you're using given information in order to solve for c. Like you're using, we call that the initial value in order to solve for c and find a particular solution. So now we're adding to our toolbox a method that will allow us to solve differential equations that can be written in a particular form. Now, you're not always going to see the differential equation in this form. I kind of relate it to, how like an equation of a line you might see in standard form sometimes, or you might see in a slope-intercept form, or y is solved for, or point-slope form. But you're not necessarily going to see the equation of a line in one set form. It's just the fact that it could be written in that form. So that's what I mean here by differential equations that can be written in this form. So m of x plus n of y times dy over dx equals to 0 can be solved by a method called separation of variables. And it's called separation of variables because it involves getting all the x variables on one side of the equation with dx and all of the y variables on the other side of the equation with dy. And then we integrate. So we're going to find the general solution to this equation, differential equation, and this is a separable differentiable equation. Because we are able to get y and dy on one side of the equation and x and dx on the other side of the equation. So we could think about multiplying by y on both sides of the equation and then multiplying by dx. So we would end up with y dy equals to x dx. So now we have the differential dy on the left-hand side and the differential dx on the other side of the equation. And we can think about integrating each side of the equation. Now, when we integrate with respect to y on the left-hand side, we would put y squared over 2. And you would want to put plus c, but we're going to put plus c on the side with x, so we don't need to put another arbitrary constant. So we're going to add it to one side of the equation. That's what matters. So then when we integrate x with respect to x, that would be x squared over 2 plus c. And now we can leave as is, like this could be considered the general solution set. However, if this were maybe a multiple choice question and you get to this point and this is not one of the possible answers, you could think about using algebra in order to kind of move things around. For example, we could subtract x squared over 2 from each side of the equation. And then c represents an arbitrary constant. So we could also think about multiplying by 2 on each side of the equation here. And when we do that, the left-hand side would turn into y squared minus x squared. Since that's 2, which is a constant, times c, we could almost think of the c as absorbing that 2, and it would just still, that product would still represent an arbitrary constant, which we could call c. Sometimes you'll see in textbooks where when they do this initial step where they first bring up c, they're like, oh, this is c sub 1. And so we could think, okay, well, we have 2 times c sub 1, which we can rename c. But this would be one way of representing the general solution to that differential equation, and we solved by separating variables. Okay, the next one. So notice I don't have a dy over dx there, but I do have y prime, which is the same as dy over dx. I would rewrite y prime as dy over dx. And then we already have y and dy on the left-hand side of the equation, so we can think about multiplying by dx on both sides of the equation to get it on the same side as sine of x. And then we're ready to integrate. And this step needs to be shown. This is showing that you've separated the variables. Okay, so then we have y squared over 2 when we integrate the left-hand side, and we're going to put the plus c, plus the constant of integration with the integral that's in terms of x. So when we integrate sine, that's going to be negative cosine plus c. And we could again, we would probably not solve for y explicitly here. We'd end up with 2 different equations, but we could think about multiplying by 2 on each side of the equation. And again, we can think about that c as absorbing the 2. So 2c is still just an arbitrary constant. So that's a representation of the general solution set to that differential equation. Okay, so you guys can try the next 2. Here, I'll write down what the answer should be. So try and get your answer for this first you try to be y cubed equals to x cubed over 3 plus 2x plus c. And then for this next differential equation, try this one as well. Try and get your answer to be y squared equals 2e to the x plus c. And let me know if you have questions on either of these. Okay, slightly different problem next because you're being asked to find a particular solution, and that particular solution is based on the initial condition that y of 1 is equal to 4. This is just, I don't know if we've really used this notation before, but this is basically function notation, where you're treating y as basically the function name, right? The output. It would be the same as if our function was f of x. So this could be thought of as like f of 1 equals to 4, or it's the ordered pair, the point 1 comma 4. Okay, so in order to integrate, we need to separate the variables. This one is in that form that I showed you guys, that differential equations that could be written in this particular form are the ones that we're able to solve by separating variables. So we would have y to the 1/2 dy, and then after subtracting x to the 1/2, we can multiply by dx. And then we are ready to integrate. So when we integrate y to the 1/2 with respect to y, we will end up with 2/3 y to the 3/2. And then integrating x, that will be negative 2/3 x to the 3/2 plus c. And then again, just thinking about if this were a multiple choice question that maybe the answer wasn't there, you might want to get might have to get your x and y terms to be on the same side of the equation. So let's say that you had 2/3 x to the 3/2 plus 2/3 y to the 3/2 equals to c. And then let's say that we want to multiply, there's no coefficients. The coefficient to each of those terms is 1. So let's think about multiplying by 3/2 on each side of the equation. which would then leave us with x to the 3/2 plus y to the 3/2 equals to, well, 3/2 times c is just going to be c. That c is absorbing the 3/2. Okay, but we're not done. This is just the general solution. And then now we want to find the particular solution for y of 1 equals to 4. So we're plugging 1 into x and 4 into y. So that'll be 1 plus, you could think square root of 4 is 2, and then 2 cubed is 8. So c ends up being equal to 9. I'm going to flip this around. Okay, so then our particular solution will be x to the 3/2 plus y to the 3/2 equals to 9. Okay, so I'm going to leave the u try here. For this particular solution, you should end up with y cubed minus x cubed equals to 8. So see if you can do that. If you need help, let me know. Okay, let's do this one. So this would be the square root of 1 minus 4x squared times dy over dx equals to x. Well, I'm going to have to divide by the square root of 1 minus 4x squared on both sides and then multiply by dx. So dy is going to look like it's by itself on the left-hand side of the equation. But that's okay. We can still think about integrating, and that's the same as integrating 1, right? So we'd actually end up with y equals. Now to integrate the right-hand side, it makes it look like we might want to use arc sine or something, but the formula, but that actually doesn't work here. This is actually just a u sub problem. Where we can let u equal to 1 minus 4x squared. Du over dx is equal to negative 8x. So du over negative 8 will be equal to x dx. Right? X dx we can then replace with du over negative 8, which is negative 1/8. Times the integral, that'll be u to the negative 1/2 du. And then negative 1/8 is there. That'll end up being 1 over negative 1/2 plus 1 will actually end up being 2. So 2u to the positive 1/2 plus c. And then just finishing substitution. So substituting 1 minus 4x squared back in for u. So negative 1/4 times the square root of 1 minus 4x squared. Is this finding a particular solution? No. Plus c. So using what we already know, and then our new skill of separating the variables. Okay, so this is one we step it up a notch. Not really, but kind of. Okay, so y prime I'm going to rewrite as dy over dx, and I'm also going to rewrite that as x to the 1/2, and I'm going to think about dividing by y on each side, or which is the same as multiplying by 1 over y. So then I'll actually multiply by dx on both sides too. Here we go. We've separated the variables. So we're ready to integrate. Now when we integrate 1 over y, that's natural log of absolute value of y. And this is where it gets a little bit tricky. And then what that'll end up being 2/3 x to the 3/2 plus c. Now, this is technically the general solution set. However, for application purposes or just the way that you would probably see this come up would be the solution written as y equals, so that you could see the solution as a function, an equation that represents a function. So we can do that by using our logarithm properties. Now remember, for logs, if you have log base b of x equals to y, that can be rewritten in its equivalent exponential form, thinking b to the y power is equal to x. Okay, so doing the same thing here, natural log is base e, so e to this power is equal to, that's absolute value of y. So we have absolute value of y, switch back to blue here. Absolute value of y is equal to e to the 2/3 x to the 3/2 plus c power. Okay, now using some of our exponents knowledge, exponent properties. Since the exponent has addition happening, we can actually rewrite this as e to the c power times e to the 2/3 x to the 3/2. We usually think about this going in the reverse, right? If we have a base raised, here I'll do this in a different color. So if we have a base raised to the m power times a base, the same base raised to the n power, that's equal to b to the m plus n power. And we just went in the reverse. We went this way. Okay, so from here, you should recognize that e to the c, or you could recognize now, I'm going to point it out to you. C is an arbitrary constant. E raised to a constant is still a constant. So e to the c is still just c, an arbitrary constant here. Okay, c just represents a constant. Okay, to get rid of the absolute value bars here, we would say that y is equal to plus or minus e to the c times e to the 2/3 x to the 3/2 power. Well, guess what? Plus or minus e to the c, like e to the c would be positive, plus or minus would say that e to the c is positive or negative. And we are still able to think of this as still representing just that constant of integration, c. Okay, so here is the general solution to that equation. Okay, you guys can try this one on your own, and the answer that you should end up with would be y equals to c times e to the 4/9 x power. Okay, we'll do this one together. So just thinking, this is same thing we've been doing, but looking at it as is, and notice the directions say solve the separable differential equation. So it's basically, it's telling you the method to use to solve this equation. And the fact that this is separable, even though it doesn't look like it initially. So then you're like, okay, well, how can I rewrite this in order to separate the variables? Well, e to the x minus y, thinking exponent properties, that's the same as e to the x over e to the y. So then we would have e to the y dy equals e to the x dx, and we can think about integrating each side of the equation. And when we integrate e to the y, we get e to the y. And when we integrate e to the x, we get e to the x plus c. Okay, we want to get to y equals, so we could think about taking the natural log of each side of the equation here. And then the left-hand side would just become y, right? Like thinking about taking, I'll write that step out. Thinking about taking the natural log of each side of the equation. The left-hand side is just y. So y equals to natural log of e to the x plus c. And that is our general solution. We have y equals. Okay, so this is a little bit of practice. This is from the Hawaii version of the 2006 AP Calculus AB exam. So notice we're given a differential equation, and the first question is asking to sketch a slope field for the 9 points that are indicated. Okay, I'm going to quickly sketch this. Now, I will point out that looking at this equation, if we were to set dy over dx equal to 0, we could easily identify that y equals to 1 would make dy over dx equal to 0. So that means along the line y equals to 1, there are horizontal tangent lines. Okay, and then you could make a table of values for the other points. I don't know if there's really trends that are happening. You could see if you could spot anything. It's not really that many points. So x, y, and then dy over dx. Okay, so if we were to plug in -1, -1, so starting with the bottom left corner, that would end up being, well, -1 minus 1 would be -2 squared would be 4. And then cosine of negative pi is the same as cosine of pi, which would be -1. So we get -4. So pretty steep slope. And then -1, 0. That'll end up being 4 times cosine of 0 is +1. So that ends up being, oh, sorry, -1, 0, sorry. Plugging 0 in for y, so that would actually end up being 1 times -1, which is -1. So aiming towards the point, I'm aiming towards the point 0, -1 in order to graph that line segment. Okay, and then how about 0, 0? So if y is 0, that's going to be 1 times cosine of 0, which is 1. So that's a slope of 1. When I graph that line segment, I'm aiming up towards 1, 1, and down towards -1, -1. And then 0, -1. So that'll be 4 times 1, which is 4. +4. Okay, make sure that looks more steep than the slope of 1. And then at 1, 0, that would be 1 times cosine of pi, so -1. Oops. And then 1, -1. So that will be 4 times -1, so -4. Okay, so there's my slope field. Part B says there's a horizontal line y equals to c that satisfies this differential equation. Well, we kind of already answered that. We're able to see the horizontal line. Y equals to 1 satisfies this differential equation. Right? When y is equal to 1, dy over dx will be 0 for all values. So we can say for part B, you could say y equals to 1 satisfies the differential equation, or we are able to see, here we could say y equals to 1, I'll write that up, satisfies, using their language, the differential equation so c is equal to 1, because it says find the value of c. It doesn't say that we have to do anything else, but we're able to see that that would be a horizontal line in the graph. Okay, or in our slope field. And then for find the particular solution, y equals to f of x. Notice y equals. So our particular solution should be of the form y equals to our differential equation where our initial condition is f of 1 is equal to 0. So looking at the differential equation that we are trying to solve, we need to separate variables. So I'm going to divide by the quantity y minus 1 squared on each side and multiply by dx. And then we can integrate. Now, to integrate each side here, we need to use u subs on each side. So we would let u equal to y minus 1 on the left-hand side, and du over dy would be equal to 1, so du equals dy. That means we'll have the integral of 1 over u squared, which is the same as u to the -2 du. And then on the right-hand side, I'm going to use a different variable. I'm going to let, I don't know, like z equal to pi times x. So dz over dx is pi. dz over pi is equal to dx. So we'll have 1 over pi times the integral of cosine of z dz. And then we are ready to integrate. So integrating on the left-hand side, that'll end up being negative u to the -1st. And then when we integrate cosine, that'll be 1 over pi sine of z plus c. And then we need to remember to substitute back in. So -1 over y minus 1 equals to sine of pi times x over pi plus c. And then it probably makes the most sense to solve for c now. So plugging 1 in for x, 0 in for y. When we do that, we'll get 1 on the left-hand side, right? Because -1 divided by -1 will be just +1. And then we're plugging 1 in for x. So sine of pi is actually 0, so we just end up with c being equal to 1. That's our constant. So plugging 1 back in for c, Okay. And then thinking about multiplying both sides of the equation by y minus 1. Is that what I want to do? Yeah, we can do that. Plus 1 times y minus 1. And then I'm trying to isolate y. So from here, I can think about dividing by sine of pi x over pi plus 1. That's yucky. And then adding 1. Before I add 1, I'm going to think about multiplying by pi over pi. Get rid of complex fractions. So that's negative 1 over sine of pi x plus pi plus 1 is equal to y. And that is our particular solution. To this differential equation. Okay, and I put a note here. There's more examples in your textbook on these pages if you want to check them out. I think this is a good stopping place, so I'm actually going to make another video just so that this isn't super long. So see you in a second.